All right, let's dive right in. Today, we're tackling two of the most powerful concurrency patterns you'll find in Go, worker pools and rate limiting. Stick around because by the end of this, you're going to know exactly which one to reach for to make your Go applications more stable, more efficient, and just plain better. Let's do this.
So have you ever been there? You spin up a ton of Goroutines thinking, this is going to be so fast. And then you just watch in horror as your app's memory shoots through the roof and everything just stops. Or maybe you've seen that dreaded 429 too many requests error pop up from an API you're hitting. Sound familiar? Yep, these are classic signs of concurrency running wild. And today, we're going to learn how to get it under control.
Here's how we're going to break it down. First, we'll talk about what this concurrent chaos really is. Then, we'll look at our first solution, the worker pool. After that, we'll check out rate limiting. We'll put them head-to-head to see when you'd use which. And finally, we'll wrap up with the absolute key takeaways you need to remember. Okay, Section 1, Controlling Concurrent Chaos. You know, the goal here isn't just about making things run faster. It's about control. It's about managing your resources so you can build systems that are predictable and stable. So, let's get into our first major tool for taming that chaos, the worker pool. This is probably one of the most common and useful concurrency patterns you'll see out there in the Go world. So what is it exactly? Well, at its core, a worker pool is just a fixed group of Go routines, or workers, that are all ready to do some work. And they all pull their tasks from one single shared queue. And in Go, that queue is almost always a channel. Simple as that. The best way to think about this is the supermarket analogy. It's perfect. The jobs you need to do, those are the customers. They all line up in one single line. That's our jobs channel. And the checkout cashiers, those are your worker Go routines. The key here is you don't have a million cashiers. You have a fixed number, right? This keeps things moving smoothly without the whole store descending into chaos. So why bother with this pattern? Well, it directly solves those problems we talked about. First, resource control. Because you have a fixed number of workers, you stop your app from eating up all your memory and CPU. It's a lifesaver. Second, it just gives you a really clean, organized way to manage tasks running in parallel. And third, it naturally limits your throughput. You can only get work done as fast as your workers can process it. So, let's look at some code. A classic worker pool basically has a few key parts. You create a channel for the jobs, you start up a bunch of worker Go routines that are all listening to that channel, you push all your jobs onto the channel, and then, this is important, you wait for them all to finish up before your program exits. Let's break down the worker function. This is the heart of the whole thing. It's really just a for loop that ranges over the jobs channel, pulling out work as it comes in. Now, see that defer wg.done? That is absolutely crucial. The wg is a wait group, which is just a fancy counter. wg.done tells the main program, hey, I'm done with my work. This is how we keep track of everything. And in our main function, we're managing the pool. It's a three-step dance. First, for every worker we start, we call wg.add1 to increment our counter. Then, after we've sent all the jobs, we must call close jobs. This is like telling the workers, all right, folks, no more work is coming. If you forget this, your workers will wait forever. That's a deadlock. Finally, we call wg.wait, which just blocks and waits until that counter hits 0. Awesome. So we figured out how to control the number of things happening at once. But what about controlling the speed? You know, the frequency at which things happen. Well, that brings us to our second incredible tool, the rate limiting pattern. Rate limiting is exactly what it sounds like. It's all about putting a speed limit on certain operations. How many times can this happen per second or per minute? This isn't just a nice to have. It's absolutely essential for building systems that have to talk to the outside world or protect themselves from getting swamped. And the reasons for this are super practical. You use rate limiting to protect your own servers from getting hammered. You use it to play nice with other people's APIs so you don't get blocked. This also means you control your costs on paid services. And it promotes fairness, making sure one hyperactive user can't ruin the experience for everyone else. Now, you won't find a rate limiter in Go's core standard library, but the community has a clear favorite, the golang.org/x/time/rate package. It uses a really cool and easy-to-understand algorithm called the token bucket. Just picture a bucket. Tokens are dropped into it at a steady pace. To do anything, you have to grab a token first. If the bucket's empty, you gotta wait. The most straightforward way to use it is with the wait function. This call will literally pause your code. It blocks everything until a token becomes available. This is perfect for when you know you have to do the thing eventually, you just need to slow down a bit to stay under the limit. But what if waiting isn't an option? What if you need an answer right now? For that, we have allow. Instead of blocking, it just gives you an instant yes or no, a simple Boolean. This is great for when you'd rather just drop or reject extra requests when you're getting slammed, instead of making everyone wait in a long line. So here's the senior engineer's choice right here. You use wait when you want to apply back pressure, basically slowing down the source of the work because you can't keep up. It guarantees everything eventually gets done. You use allow when you need to shed load, when you're under attack or just too busy, and it's better to say no to new requests than to bring the whole system down.
Okay, we've got 2 awesome patterns in our toolbox. But the real skill is knowing exactly which problem each one is built to solve. So let's put them side by side and see what makes them tick. This table makes it all crystal clear. A worker pool is about the number of concurrent tasks. Think how many supermarket cashiers are open. A rate limiter is about the frequency of events. Think how fast is that faucet dripping. One uses a pool of goroutines, the other uses a token bucket. You'd use a worker pool for crunching through a huge batch of background jobs. You'd use a rate limiter when you're building a client for an external API.
We've covered a ton of ground, so let's boil it all down to the most important things you absolutely need to walk away with today. For worker pools, burn this into your brain. Number 1, it's all about controlling the number of goroutines. Number 2, the key ingredients are your goroutines, a channel, and a sync.wait group. And number 3, the golden rule. Always, always, always remember to close the jobs channel when you're done. No excuses. And for rate limiting, it's just as simple. 1, it controls the frequency of events. How often, not how many. 2, just use the golang.org/x/time/rate package. It's the standard for a reason. And 3, choose your weapon. Wait when you need to block, and allow when you need a quick yes/no answer. I really want to leave you with this quote from Rob Pike, one of the creators of Go. He said, "Concurrency is not parallelism. It is about dealing with lots of things at once." Think about that. These patterns aren't just about making things go fast. They're about giving us the structure we need to deal with complexity in a sane and manageable way. So there you have it. But I'll leave you with one final thought to chew on. These tools aren't mutually exclusive. So how could you combine them? What if you had a worker pool, but inside each worker, you placed a rate limiter? That would control how many API calls you're making in total, and how fast each individual worker is making them. The real magic happens when you start putting these powerful ideas together.